Hey everybody, Jonathan here. In this video, I'll be giving you my take on section 11.9, which is all about representing functions as power series. Now in the last section, we learned that power series are a new way of defining functions. However, it's actually incredibly useful to look at our currently known functions and ask, is there a way to represent those as power series? Because in many instances, it's actually easier to deal with a power series than it is to deal with defining a function some other way. So the first example of this comes from the formula we have for geometric power series. Recall that the series 1 plus r squared and so on and so on and so on is equal to 1 over 1 minus r, provided that the absolute value of r is less than 1. If we replace r with the variable x, then it tells us that the function 1 over 1 minus x is equal to the power series 1 plus x squared and so on, so long as the absolute value of x is less than 1. So this is the first function that we now have represented as a power series. Now I'm going to illustrate this graphically for you all. So in blue here, we've got the graph of the function 1 over 1 minus x. Now remember, when we represent it as a power series, the radius of convergence only goes between x equals minus 1 about here and x equals 1 about here. Now, there's no way of having a function be a power series and having Desmos be able to graph it for us. However, what we can do is we can come up with the approximation just by adding in the first few terms. So remember, this is the power series 1 plus x squared and so on and so on and so on and forever. Well, if we only add up the first n terms of that, then we should get a decent approximation. So when there's just one term, then in green we've got our power series approximation, and it's not that good. But I can move this slider up, and already you can see that when n equals 1, it was really only good around this one point at 1. But when n equals 2, look how closely the functions are agreeing in this region. And remember, we only expect it to converge between minus 1 and 1 because that's the radius convergence, only between here and here. And now when n goes to 3, it'll get to be a little bit better. When n equals 4, it'll get to be a little bit better. The idea is that the blue graph and the green graph are going to get closer and closer to each other as I increase n. So we'll just go a few more flips. Right now at n equals 10. I mean, we can't quite get all the way out to minus 1, but on the right-hand side, like, look how closely that mirrors. If we zoom out, well, the things are so big, you can see them splitting up a little bit up here. But at least when you're close to 0, these curves are almost identical. Now, this is just one function, but by replacing this x with other expressions, other functions of x, and then you can replace all the x's over here with the same thing, we'll get a lot more power series out. So for example, if we replace the x with, say, a minus x squared, we can get the power series for 1 over 1 plus x squared. As you can see, they replace the x with minus x squared, and you replace all the terms in the power series with minus x to the 2n to the n, and that simplifies to this minus 1 to the n, x to the 2n. Now, illustrating this graphically, in the green, we have the function 1 over 1 plus x squared. And now in the blue, when I turn it on, we can see that corresponding partial sum of the power series. And this is just for n equals 1. And even for n equals 1, you can tell the radius of convergence is still 1, but you can tell that close to 0, we already have a very nice approximation. And by increasing n, the overlap of these curves will only get greater and greater. It'll keep moving out closer and closer and closer and closer to minus 1, 1. It turns out n has to be quite large to get it so that you can't distinguish it even like at 9, but still, as you can see, as n grows, the graphs match along a bigger and bigger section of the curve. Now, one awesome thing about power series is that they are basically polynomials. They are infinite polynomials, and as a result, they are very, very simple to calculate derivatives of and to calculate integrals of. You do it just like they were a polynomial. So here, if you differentiate x minus a to the n, just one term of this, you of course get n times x minus a to the n minus 1. So therefore, the derivative of the entire power series, the sum from n equals 0 of cn x minus a to the n, is simply the sum from n equals 1 to infinity of n times cn times x minus a to the n minus 1. Could not be simpler. You don't have to bother with the 0 term here. You certainly could include 0, and maybe they should for cleanliness, except that when n equals 0, the term's not there because of that n. And then integrating is just as easy. If we just have cn times x minus a to the n, and you want to calculate that thing's integral, it's just going to be 1 over n plus 1 times cn times x minus a to the n plus 1. You do that for all the terms, and we therefore get the integral of our power series is just some constant. You can't forget the constant. We usually put it in front now because it's sort of more confusing to put it to the right. But nonetheless, the integral of this power series, we just integrate each term like it was a polynomial, and we get that it's c plus the sum from n equals 0 to infinity of cn times x minus a to the n plus 1 all over n plus 1. Again, it's as simple as differentiating or integrating a polynomial. Now, as a totally awesome application of that, remember that we know the power series for 1 over 1 plus x squared, and we also know that that's the derivative of arctangent of x. So by integrating this power series, we'll get a formula, a power series representation for arctangent of x, which is so useful because how the heck else are you supposed to find arctangent of any but a few numbers? And it turns out you can just approximate it using the power series. Sadly, the radius convergence is still only minus 1 to 1. But nonetheless, that's enough to work with. Even for numbers outside that range, there's tricks you can do to get a nice power series representation and be able to approximate it. And how do you think your calculator finds things like arctangent? It uses a series like this. So just to be clear here, we've now got that arctangent of x by integrating this series, and then by figuring out the constant by plugging in an actual value for x, which gets the usually you want to plug in x equals 0. We get that arctangent of x is exactly the series, the sum from n equals 0 to infinity of minus 1 to the n times x to the 2n plus 1 over 2n plus 1. Though sadly, the radius of convergence is only 1. Now, we can see what this looks like on Desmos. In black here, I've got the graph of y equals arctangent of x. And remember, it's just that nice looking curve with a horizontal asymptotes, y equals minus pi over 2 on the left and y equals pi over 2 on the right. And if we turn on our power series way of representing it, even when n equals 1, you can see we've actually got a pretty darn, look how close these curves are. Look how close they are between, say, minus a half and a half. Now, sadly, as I increase n a little bit, we will get a better and better approximation. This is actually converging a lot faster than the other ones. Already by n equals 7, it's almost a perfect match, except quite close to minus 1 and quite close to 1. However, no matter how big you make 7, there I am making it, no matter how big you make n, you're never going to get it to match past minus 1 and 1 because of that radius of convergence. So power series are pretty exciting, and on this page here I have a bunch of the power series for things derived from the 1 over 1 minus x power series, and you can turn them all off. You can adjust n as you like and watch things get closer and closer, at least between minus 1 and n. And furthermore, once you see what I've done, it's easy enough to add your own. So feel free to use this Desmos page. I'll include a link to it. Otherwise, have fun, and I'll see you in the next video.